Hello everyone and welcome back. So in this particular lecture we are going to learn a very interesting theorem on Laplace transformation. So you already know about 5 different theorems or properties in Laplace transformation in our earlier videos, but this is a special theorem. So first we'll see how we can prove this particular result, and we'll see some applications of this, very important applications of this particular theorem. Now what the theorem says, if the Laplace transformation of f of t is f of s, now see, just observe it very carefully. In place of f of t, if it is f of t by t, it cannot be t square or something else, only t. F of t by t. Now what is the right hand side? You just observe it very carefully. The limit is not 0 now. It is from s to infinity f of s ds. Okay. So if it is L of f of t, then it should be 0 to infinity e to the power 0 to infinity f of s ds. But here it's completely different. Okay. So let's see how we can prove this. So you all know that f of s means Laplace transformation is what? 0 to infinity e to the power minus st, and then what? F of t dt. Then what we'll do? We'll integrate both sides with respect to s from the between the limit better right, integrating both sides with respect to s from s to infinity. So we are changing the limit. Okay, so now it is from s to infinity f of s ds is equal to first integral will be s to infinity, then there is one more integral. For this we have to write ds, then 0 to infinity e to the power minus st f of t dt. Okay, so what is extra here? This particular integral with respect to s. Okay, now we know from the definition that s and t both are independent, so one is not depending on other. So this particular integration you can write like this: 0 to infinity, then f of t dt, and then s to infinity we are just replacing the integral like this: e to the power minus st ds. Okay, so that means we are separating t and what? S. Then first integral will be as it is, f of t dt, and we can integrate this. We know that e to the power minus st is e to the power minus st by how much? Here we are integrating with respect to s, so it will be minus t between the limit 0 to, not 0, between the limit s to infinity. Now it's very interesting. You see, if we put infinity, e to the power minus infinity is 0. Okay, but whenever we will put s, then it will remain same. Means what I'm meaning, dt let us write on the back side. So if we put infinity, it is 0, and if we put s, then it will be minus st by t. Okay, dt, minus st by dt. So one minus is already there. If we put the lower limit, then one more minus, so it will become plus. So what finally you have now, you see, 0 to infinity e to the power minus st, and let us write ft and t together dt. So how it looks like? 0 to infinity e to the power minus st, and let us suppose this is f of t. Okay, 0 to infinity e to the power minus st f of t. So how will write it? Laplace transformation of f of t. Our f of t is f of t by t. So this is the theorem. If Laplace transformation of f of t by t is how much? S to infinity f of s ds. Okay, so this is a very important property, and we have some very good application of this particular theorem. Let us see in this particular example. Find the Laplace transformation of sine at by t. Okay, sine at by t. So here f of t is sine t, and this is our t. So how will start? Here f of t. So our f of t is sine at, and then t is separate. You can find the Laplace transformation of sine at. It is how much? A divided by s square plus a square. So this thing we have to use later. So by that particular theorem, by the theorem, what we can write by this particular theorem? Laplace transformation of, or you can write better like this. We have Laplace transformation of f of t by t. Let us mention the theorem so that it will be easy for all of us. The note is inside f of s ds. So we'll use this particular theorem. So Laplace, our f of t is sin at by t. Then it is s to infinity. Now what is f of s? F of s is this one, Laplace transformation. This is our f of s, right? So how much it is? It is a divided by sin at and then what? ds. Okay, a divided by sin, if it is s, then sorry, I'm writing it wrong. It is s square plus s square. Okay, s square plus a square ds. Now we have to just simply integrate it. A is constant, so take it outside. This is of the form integration dx by x square plus s square. What is the formula? 1 by a tan inverse s by a between the limit s to infinity. So a cancel out. So if you put infinity, tan inverse infinity is how much? Tan inverse infinity is our pi by 2. Then minus, it will be your tan inverse s by a, because both the s are same. So there is one rule, no? Pi by 2 minus tan inverse x is what? We can write cot inverse s by a. Okay, cot inverse s by a. So this is the answer. It's very simple result. Now using this particular result or problem, we can do some other problems also. See this particular problem, it almost looks like same. So sin t by t. So what is the first problem? In our first problem we see that it is sin at by t. Okay, there is one more part, cos at by t. So cos at by t. So in the same way, cos at by t will be our s to infinity. When it is cos, it is s divided by s square plus a square. How much? ds. Okay, so the formula will be half into log. If we integrate it, exactly this term will get between the limit s to infinity. But there is one problem. If you put infinity, no, log infinity is undefined. So that's why it is does not exist. Okay, it does not exist because limit will be what? Infinite. Now using this particular result, I'm talking about this Laplace transformation of sin at by t. So using this particular result, we are going to do some problems. Okay, so remember this sin at by t is how much? Cot inverse s by a. Now see, using the previous problem, we can solve this particular problem. Prove that 0 to infinity e to the power minus t sin t by t dt equals to how much? Pi by 4. So in the previous problem, we have like this, sin at by t. Okay, sin at by t is equals to, what is the answer? Cot inverse s by a. This one we got here, right? Laplace transformation of sin at by t is equals to how much? Cot inverse s by a. So this particular result we are going to use here. No, this is of the form L of f of t, right? You just see the left hand side, L of f of t. So what is the formula for L of f of t? 0 to infinity e to the power minus st, then f of t, our f of t is sin at by t dt. And right hand side is as it is, cot inverse s by a. Okay? So in left hand side, what we have used? The formula for Laplace transformation of f of t. So this we consider as f of t. Now to get the answer, what to put? Putting s equals to 1, because if we put s equals to 1, we will exactly get this minus, and then a is also 1. So what we get now? 0 to infinity e to the power minus t sin t by t dt is equals to, what is the right hand side? Cot inverse s is 1, a is also 1. So how much it is? For cot inverse a is how much? Pi by 4. Okay, so let us take one more example. So here it's same. similar kind of problem, but here there is no e. So again we have Laplace transformation of sin at by t is equals to how much? Cot inverse s by a. So in the left hand side we use Laplace formula 0 to infinity e to the power minus st f of t is sin at by t dt is equals to how much? Cot inverse s by a. To get this particular answer, what to put? We have to putting s equals to how much? There is no e na. S equals to 0 and t equals to what we can put? T a equals to what? 1. So it will be 0 to infinity e to the power 0 is 1. So we get sin t by t dt, and then if we put 0 on the right hand side, no, cot inverse 0. Cot inverse 0 is how much? Cot inverse 0 is pi by 2. So okay, so the theorem and the applications are almost similar and it's very easy also. So I hope you understand this particular theorem and their application. So if you like my videos, kindly subscribe and share with your friends so that others also can the same benefit. Thank you for watching.